This video is going to be about dividing monomials. So like a single-termed polynomial, that's a combination of numbers and variables raised to positive whole number exponents. And mostly knowing what to do with the exponents especially. So to kind of discover the properties that we're going to use, I have 4 examples here, 2 with numbers as the bases. So remember, an exponential expression, you have a base. So these are the same base raised to exponents. So I have numbers as bases, and then below I have variables as bases. Now to figure out how I can simplify this, I'm going to expand it. So 2 to the 4th means to multiply by 2 4 times. So I'm just that's expanding it, writing it out in a less convenient way. Like exponents are a nice way to clean up multiplication. And then 2 to the 2nd is 2 times 2. Now I have all these 2's divided by these 2's, and I know that 2 divided by 2 is just 1. 2 divided by 2 is 1. So those reduce down to 1. And I'm left with just 2 times 2, which is the same as 2 to the 2nd power. So my goal here is to figure out and show you how to rewrite this as the base to a single power, how to combine, almost like how there's that product property that if I had 2 to the 3rd times 2 to the 5th, they would become 2 to the 8th. I want to show you, okay, what do I do when it's not a product but a quotient? So let's try this next one with x's. So this is x 5 times 1, 2, 3, 4, 5 divided by x. So one of them reduces, and I'm left with these, and that is x to the 4th power. Okay, so take a second and think, can I come up with some general idea? I have 4 and 2 and it becomes a 2. I have 5 and 1 and it becomes a 4. Let's see some more. 3 squared over 3 to the 7th, so that's 3 times 3. And then 3 7 times. All right, so 2 of these reduce down to 1. And so all I have left in the numerator is a 1. And what I have in the denominator is 1, 2, 3, 4, 5 3's. So I could write that as 3 to the 5th power. So this becomes 1 over 3 to the 5th power. So notice how I had 2 and a 7, and I end up with a 3 to the 5th. So maybe you're thinking, oh, subtraction, like if certain amounts are reducing, I can generalize that with subtraction. Let me do one more. So I'm going to do it without expanding because that's the ultimate goal. I can only reduce things with the same base. Like I can't cross out a 3 and a 7. It has to be the same. So I can't reduce the x's and y's. I have to just look at the x's. So first I'm going to look at x squared over x cubed. So this is x times x in the top, and this is x times x times x times x in the bottom. 2 on the top, 3 in the bottom. So if I were to expand that and reduce, I would be left with 1 in the bottom. And also realize 3 minus 2 is 1. If I have 5 y's on the top and 1 on the bottom, and I expand that and reduce, one of them will reduce, and I'll be left with y to the 4th on the top. 5 minus 1 is 4. Okay, so I made a big fraction bar. I ended up not needing it because that's just going to reduce to y to the 4th over x to the 1st. So this is how you deal with expressions that have exponents. Realize that if I had coefficients, like if I had 12 over 18, I would still reduce like I always did. Now, common fact, you don't really write this out anymore, but it's just 3 times 4 and 3 times 9. So the 3's reduce, and 12/18 reduces to 4/9. Like, those division rules are still in play, this is just showing you, okay, what do I do when I have variables or numbers to exponents? How do I reduce? So I'm going to give you a general rule. So there's a lot on this slide. We're just going to look at the top for now. So if I have a to the m over a to the n, and if m is bigger than n, so this is the bigger one. So like if I had a to the 10th over a squared, so the m is bigger. If m is bigger, you have more a's on top. You're going to just do the bigger number minus the smaller number, and it's going to end up in the numerator. Because you had more a's in the numerator, you're going to be, once you reduce, you're going to have more like a's left over in the numerator. Okay, so now if m is less than n, so n is the bigger number. Like if you have a to the 2nd over a to the 12th, so n is the bigger number. This is, so I have more a's in the denominator. That means all the leftovers are going to be left in the denominator. And you're always going to do the bigger minus the smaller. Bigger minus the smaller. Okay, so let's see some examples. So I'm going to start with number 1, 9z to the 7th over 3z squared. Now the numbers out front, you don't have any like rules for this. This is what you've been doing for years, just like 9 divided by 3. So usually a good thing to start out with is just drawing your fraction bar. So 9 divided by 3, that goes in evenly, is just 3. Now I have z to the 7th over z squared. So that matches this one, where the exponent on top is bigger. I have 7 z's on top, right? Z multiplied by itself 7 times, and on the bottom, z multiplied by itself 2 times. So 2 of those z's will reduce, and I'll be left with z to the 5th. So this 5 came from 7 minus 2. Okay, so there ends up being no denominator because it reduces. And you can just say your answer is 3z to the 5th. Okay, let's go on to example 2. So often these problems will involve many rules. The product rule, quotient rules, like all these different ones. So I have the same base multiple times here. I have x's. And your problem's not fully simplified if you see the same base multiple times, because you can always combine it. You can multiply with the same base, you can divide with the same base. So I have 3 x's here. I know my final answer. I should just be writing this as x to a power. So what I'm going to do in the top is use the product rule first, that if I'm multiplying with the same base, I keep the base and add the exponents. So I'm not afraid of that negative exponent. If you haven't gone over that yet, it's okay. You're just going to add the exponents, and you happen to be adding an exponent that's negative. That's fine. Over x to the 8th is the same. Okay, so now I have the second version of this kind of quotient property here, or division property. I have x times x in the numerator and x times x times x, 8 times in the denominator. So 2 of my x's will cancel, and I'll be left with x to the 6th in the denominator. You can kind of think like who wins, who's bigger, and that's where your exponent's going to end up. Wherever there's more, once you reduce, that's where the leftovers are going to be. Just make sure you put a 1 in the numerator. If there was nothing else here, if there was more stuff, it would still be in the numerator, but there's nothing, so you have to put a 1. That x to the 6 can't magically come up to the numerator. It's still in the denominator. Okay, so let's do the next one. And this part has 3 pieces I can combine. I can simplify 25 over 15. I can simplify p to the 12th over p to the 12th. And I can simplify v to the 19th over v to the 12th. So 25 over 15, its common factors are 5, so that's going to be 5/3. So 5/3. That just reduces like normal. I'm not subtracting. The subtraction is just for exponents from expressions with the same base. P to the 12th over P to the 12th. Now I could subtract and I would get P to the 0, but we know that's just 1. We also know anything divided by itself is just 1. So you could get to the fact that P to the 12th over P to the 12th is 1 two different ways. The fact that it reduces with this rule to P to the 0, and anything to the 0 is 1, or anything divided by itself is 1. That's actually why anything to the 0 is 1. It just works with these exponent properties. And lastly, I have V to the 19th over V to the 12th. So that's this version. The 19 is bigger than the 12, so I'm going to end up with V's left over on top. Specifically 19 minus 12 of them, which is 7. So my final answer is 5V to the 7th over 3. Great. Okay, so now I'm going to do this last one. And I'm not going to use negative exponent properties. I'm going to just use this general rule and think about, okay, I have two exponents, -2 and 8. Which one's larger? Well, and by larger, I mean like more to the right on the number line. So if this was like +2 and -8, +2 would be bigger. But 8's bigger. So I'm going to be left with y's in the denominator. And I'm going to do n minus n, which is y to the 10th. There you go. So you can almost think like, which one's bigger and how far apart are these numbers? They're 10 apart. -2 to 0 is 2, plus another 8 is 10. So y to the 10th. Or you can do the subtraction. I just like to think like, how far apart are these? And that achieves the subtraction. There you go.